The perfect topic for the morning after BeerConf, creating a data-oriented parser/AST/visitor generator. This sounds pretty technical. Robert, it's all yours, mate.
Thank you. Good morning, everybody. So yeah, Ethan missed the important part, good fun. So that's in the title as well. For the last couple of years, I usually have been presenting on stuff I did for work. And this is not that. This is just stuff I like to do, which I think is good fun. I really like writing parser generators. I think it's awesome. The interesting thing is, though, I don't need them. I needed a parser generator once, and I used it, and it's okay. And I don't really like to do something useful with it. I usually stop somewhere after the AST part, like sort of doing the code generation that Walter did and actually getting something that executes. That's not that much fun for me. So let's really stick to the fun parts here. And if that's not fun for you, well, drink coffee, have a relax or whatever. In the good old days, when you use Yak or something similar, you get something like this. You sort of put your grammar in, and then there's a block of code that you can execute. Also, there are some dollar symbols in there, and you really have to know what to do. And you don't really get much for free. You basically get a parser, and that's it. But you don't get an AST, you don't get a visitor, you don't get a Lexer. You sort of really limited in the options of what you can get. I sort of wanted to do a bit more because creating the AST, I find, is very linked to the parser itself. So if you change your grammar, chances are that your AST is changing as well, which also means that the visitor is changing as well, or the classes that are sort of using the visitor have to change. And I thought, well, how hard can it be, right? Famous last words as always. And I sort of tried to do a thing where you put in a grammar, you get out a parser, you get out the AST classes directly, and you also get a visitor that you can subclass. And that's basically what resulted in a thing I called Darser. The name is really shit. It's basically parser with a D in front, so it must be in a good programming language. And I used that for my GraphQL implementation, and it just works fine. You get an AST out, the grammar is fine, you put it in, you have a visitor. And then this one was the actual instance where I had to do something with a visitor to actually finally execute the queries I got with GraphQL. The grammar, I was young and naive, and I used YAML as an input language. Basically, the idea is the definition is sort of the overarching name for the rule. And then there are three sub-rules, O, F, and T, because obviously typing is difficult. So O is for the operation definition. So you can actually in GraphQL define operations like this is my mutation, and it's taking this argument, these arguments, and then it's sort of crewing these elements. You can also define fragments, which is a fancy term for macros, basically, because the GraphQL people also apparently don't like writing. So you can basically create a block that you can insert into different places. And also, as it's a type query language, you also are able to define your types. This basically does it. The stuff after the hash is a name for the elements in the AST. So you get to name the elements in the AST. And if you put that into Darser, you get, among other things, one class called definition that is inherited from Node. It has a rule, which is basically an enum with the elements, what was it, O, F, and T. And you have the three sub-elements of the production. So far, so easy. And you do that for your whole grammar, and you're done. The class itself also has a couple of constructors to make it nice and user-friendly and easy to understand. And also, what is important, to have code completion, because this is not done at compile time. It's sort of a pre-compile step. I would think there's nothing in Darser that couldn't be done at compile time, but I've just found it more convenient to generate it ahead of time, also because it's faster, but also because you get code completion, which was the more important reason. You get a bit of boilerplate generated for the visitors, and the sort of more interesting thing, obviously, is the parser itself. So you get a parser class. For each of the rules, you get a function that gets called. Basically, the recursive descent parser you would very likely write by hand is written by Darser for you. First of all, it figures out the first set, so all the tokens that actually define where the rule starts. And then if you found the token for instance, the operation, you recurse into parsing the operation. If it's a definition, you recurse into definition, and so on and so forth. Very easy. Also, what is cool, you get somewhat sane error messages. As you know, as Darser knows what data to expect, you can at the end say, hey, I got this, but for instance, I was expecting an opening parentheses, but I got a closing one. That doesn't fit any of the rules we are currently at. So really simple so far. Like the first operation type, as I said, is basically checking the type of the current token to see if it's, for instance, here the query keyword, the mutation, or the subscription keyword, which is basically the first token in any operation in GraphQL. The visitor, again, is relatively simple. We know from the enum inside of every class or every node what nodes to follow. So we can generate a visitor. I added two things which I found to be really useful while implementing GraphQL is I have an extra callback for entering and exiting a definition, or pretty much every node, because quite often I didn't really need to know what was in the node, but I needed to know when it started and when it stopped to do some stuff in the visitors that I created. And I found this really useful. And I mean, again, I would assume if you write a visitor by hand, it will look very similar to this one here. And then if you want to have a visitor, and here a very small count visitor that counts the occurrences of definitions, you just do that. And I omitted the override keyword because it looks nicer this way on the slide. And the interesting bit is, I would say in general in the D community, there is a bit of hate against classes, quite often for good reason, but sometimes also not. Overriding a function and then using the super keyword to call the original implementation is extremely useful for visitors in this case, because as we saw previously in the definition, there are certain, depending on the state of the node, we have to call the visitor again with different fields out of our class. And not having to re-implementing this, but just calling super is just super. So, I mean, sometimes classes are bad, but sometimes they're awesome. And I think this is a good instance where it really saved a lot of code and makes the code easier. The recursive descent parser is basically created by taking the subrules of a rule and turning it into a prefix tree or trie, however you want to call it. That obviously results in a bit of nesting. Going from the first rule here, the TDS, so on line 2, you check that you found the on keyword. You pop that from the Lexer, you check for the name sort of in there and continue down. The cool thing about the try is if multiple subrules have the on keyword as first thing, it just sort of works out nice and the recursive descent parser really sticks out here. The only sort of difficulty there is that you have to write your rules in such a way that there is no first conflict, meaning that at some point the Darser needs to be able to decide what subrule you're actually in. And also, if you are going to like a different rule from one rule, and there are possibly multiple options, you have to make sure that there's no first conflict sort of on the first token for those rules. But Darser will complain if it finds such a conflict, but that makes writing the grammar a bit more complicated. You can insert handwritten rules in Darser because every once in a while recursive descent with like a one token look ahead is not good enough. But sure, at that point you can just write a bit of code, insert it, and Darser is happy. Yeah, this one is just continued. And at the end you can see we have again a sensible throw message there, and usually the error message that you get as a user of the library then are reasonable enough to see what went wrong. And this works, and I did most of that back in 2018 before actually getting my new job. And this was fun, and I worked on GraphQL with it, and it just works. But over time, obviously, you learn stuff, you get new interests, and for the last year and a half or so, data-oriented design was sort of creeped up on me a bit while using SQL a lot, or Postgres to be specific, and also while programming, and I realized maybe there's something to explore there. Basically, the idea is to put data that gets accessed together into a structure together into an array. Because if you look, and as we're going to look into here a bit later, performance nowadays is usually not dependent on how fast the CPU can do adds, multiplications, bit operations, or whatever. It is how fast can get your data from the RAM to the CPU, or to like L1 cache and then into the registers. Also, if you sort of looked into the database space the last couple of years, there was a big push from going in array of structs to a struct of the array. So columnar databases are now creeping up in many places and are obviously faster. So, or faster in some regards. For instance, let's say you have a big table with 15 columns, but you would just want to compute the sum of one of that column. And if you have to load the whole table from the database and you're just reading one int out of 15, let's say, obviously you're going to lose performance compared to you're just loading all the ints at once and just summing them up. It's obviously going to be faster. So basically know your access pattern will result in performance. And sort of to get an idea of that, if we do any instructions on pretty much any hardware nowadays, it's somewhat between 0.25 cycles and 10 cycles. And basically the memory that you have is all the registers, and roughly speaking, you have like 128 bytes there. And then going to L1 cache, you can already expect to wait for like 3 cycles to get the data from L1 to the registers to actually do something with that. Obviously, the size increases, but then if you go to memories, to RAM, you have to wait 100 cycles, and there are a whole lot of operations that you can do in 100 cycles. Obviously, the size of the RAM, like how much money do you have? You can buy terabytes of RAM nowadays, but the performance really comes from having the data close to the actual operations units of the CPU and operating on them without having to go to L2 or 3 memory. L1, again, is somewhat interesting. You load it by cache line. If you think about it, if you do operations on an array, most of the time, it is very likely that if you read one element, you're also going to use the next element to do some of your computations. And also, while sort of working in that space, I sort of realized 64-bit pointers are extremely wasteful. Linux, or sort of the Linux of 2024, only allows you to address 2 to the power of 48 bits. So you already have quite a few bits that are not set. This laptop only has 2 to the power of 39 bits, and it only has like 16 gigs of RAM. So who cares about pretty much 32 bits of our pointers? Maybe there's something that we could exploit. I would say uint indices are pretty much always good enough to address every memory that your program will ever need. So, and you already saved like half the size of a pointer, so yay, basically for free. But then obviously, if you sort of connect that back to the parser generator, it's called abstract syntax tree and not abstract syntax array. If you really think about it, what is a tree but indices into the ultimate array, which is main memory? Basically, you have the main memory, your nodes are sort of placed in the array called RAM somewhere randomly, and you have pointers into it. Why not think of it as one array and have indices into it? Pretty much the same thing if you think about it, minus a couple of nasty casts in there, but who cares? So how hard can it be to turn it from a tree and a class-based thing to an array and struct-based thing? Actually, it's not that difficult. So instead of having pointers to your nodes, you have uint indices. And then in the parser itself, you have a couple of arrays for each of the rule types that you have. And then you just point into that. That's my talk. Thank you. Have a nice day. But obviously, there's a bit more that we have to do. So again, taking the parser generator part here, we are still doing the parsing, but the return types, for instance, on line 4 or line 10, are no longer references to the class, but basically the subrules now return uints pointing to the array index of the thing that they returned. And then on line 6, for instance, we created a selection set for our operations definition. We append that to the array and then return the index to it on line 7. I sort of got lucky there as I implemented Darser and the outputter, sort of turning the data structures and the trie into the actual D source files. I did this via classes, so I could very easily subclass my outputter class for the original thing and turn it to this one. So I think that is another good place where classes just work fine. I mean, it's not that performance relevant generating the whole AST parser and visitor for GraphQL, which is a relatively big grammar already. I mean, it's basically when the key up event comes, the generation is done. So all good. Yeah, a bit more parsing is basically wherever you at the beginning had a class reference, you have an uint now. So that works just fine. The visitor then again is also, as you would think, instead of dereferencing the element inside of the current node we are visiting, you just get the index and reference the parser and that array and take the element out of there. Probably as most of you would have expected at this point here. Now, sort of for an interesting bit, I was really hoping to say, hey, put this switch the next time you use Darser and get like a 20% performance increase. But actually, on my laptop here for the last couple of days, I have been getting a consistent 20% performance decrease, which obviously is not the thing I wanted to present, but maybe let's think about this for a while. So I would like to start with the last line here, the memory the thing actually used. And I took the GitHub GraphQL schema definition, which is a file of 65,000 lines, so not a small grammar. With the class-based one, doing quite a few inefficient things, we already have like 300 megabytes. With the struct-based one, we reduced that to just below 200. But wall time goes up, L1 data cache loads go up, and cache misses go up. Also, it's slower. A couple of interesting things here. First, obviously, I opened up Valgrind to see where the performance is going, and parsing and actually doing the accessing of the data in a count visitor. So I implemented like the count visitor from before for every node, and basically as a debugging tool to see if the new implementation with structs yielded the same result, meaning that every node every node type was counted the same time between the class-based one and the struct-based one. And that is true. They're all counted the same way, or they're counted up the same way. The performance of the whole test goes into Lexing. So first of all, measure the right thing, meaning that the bottleneck for parsing the GitHub GraphQL grammar is definitely not the parser, it's not the visitor, it's the Lexer. Luckily, this is talk about a parser generator, which I like, so all is good. But then also, sort of a bit more reflective, you can commit no mistake, but still lose. That's not really weakness, that's just life. Sometimes it doesn't pan out. I think that also comes up in our daily lives whenever we do something. Maybe we have a good idea, maybe we think it's brilliant, maybe we think we are brilliant, but then life happens and, well, we get schooled a bit. So now I want to sort of continue the thread of data-oriented design a bit further into what else can be done, where improvements can be done, and maybe what sort of can bleed into other areas that is not just parser generation. And as I didn't have really good title for this section, I called this structured ranting. Even like the productions for the GraphQL grammar get big rather quickly, but there's always sort of the problem that the enum selecting which rule has to be stored, and that is not a uint, that is usually a byte. And I thought to myself, it should be possible to do a bit of bit mapping here to make this possible as well. D has this, it's just behind the switch, and it's not documented. And there is debate about, should we do it C-like, is it okay, is it safe, is it not? I would say this is what I would consider to be a sane use of it. Obviously, a uint with only 28 bytes is less than having 32 bytes, which is obviously true. But I think it's fine in this regard, because even though I would think that the GitHub GraphQL grammar is probably one of the biggest ones out there, 28 bits for the number of operations is still way fine. I mean, there are probably a few hundred in there, and with 28 bits, it's like 32 million or something, or 33 million elements you can index, so who cares? But then also, we can press this again into a very nice form that is easy to load into a cache line, and we can just move on. So, bitfields and structs, have another look. I think they're not as insane as we might just think. And the other interesting thing that sort of bubbled up is that if you have a tree, storing that on disk is sometimes a bit tricky, because you have to sort of follow the pointers, and then when you restore it, you sort of have to recreate the pointers. The cool thing about arrays is you can just sort of say, okay, the next thing is going to be so many elements long, and then just write that to file. And reading that again is also just the other way around. You read the first 4 bytes, you say, okay, this is how many elements of the next thing I have. As long as you don't change the ordering of your arrays in the parser during writing and reading, you are fine. And you can just sort of load that from file, cast it, and be happy. And obviously, if you do that with a memory mapped file, you can even simplify that and probably get quite a bit of performance boost. And considering that in the good old days, the HPP files, sort of the precompiled C++ headers to increase performance were a thing, and also D had a similar thing, I think storing sort of the AST raw on the disk and then just sort of memory blipping that into existence is most likely a lot faster than sort of doing it the more traditional human readable way. The interesting bit is, or sort of doing the non-so-fun part is, I really don't like writing Lexers. They're just so fiddly, and when you are sort of at the parsing stage, you have a nice rule, it all makes sense. But just think about D, for instance. If you have a number, a dot, you don't necessarily know if it's a float. It could also be another dot following, so you have a slice operation. And that is just, it just gets messy very quickly, and dealing with the Unicode symbols and all that. So Lexers are not really fun. But from my benchmarking, as alluded to earlier, there is probably quite a bit of performance that can be gained by taking a closer look, and especially taking a closer look at the token type. The current token type in the GraphQL implementation is something like this. You have your token type, you have the token itself, and the token has a value. It also stores the line and the column the token was created. But for most things, that information is irrelevant. Like, I only need the line and the column if something fails. And also for most of the tokens, the value is irrelevant. Like, I'm not going to store the opening parenthesis token and then also store the string of the opening parenthesis token. It's just there's an enum set it's to open parentheses and it's all good. So, and also it's quite a lot bigger than our uint indices that we use to index the tree itself. So again, using bitsets, we can just count the elements in the enum, say at this point 7 bits are enough to store all the possible enums. And then also we can turn the value in itself into a value or index. For the token position, obviously when we get a parse error, it would also be nice to sort of say, hey, we are here and we started that rule over there. So just basically have a circular buffer of the last, 16 token positions in your Lexer and be good. And the other thing, again, similar to how the AST nodes were stored in the parser, there are only so many value types in GraphQL that need storing. So there are ints, floats, doubles, and strings. Yeah, that's actually everything you get. So in the token itself, we have sort of a value and index. And I would say with 25 bits, you can probably store most ints that you come across in real life. So we can already sort of store that, embed it into the token, and not store the index itself, because obviously having to go to the array to get the int is going to be slower than just doing a few operations when the value is already in the registers to figure out what int is in those 25 bits. But if it's not there, you can just go to the array and get that. I said strings are also a thing, and strings don't really fit into that, because currently as this looks, you could just take the Lexer the same way as you took the parser and just write that to disk and read that from disk. But for strings, obviously, if you sort of load this GraphQL mutation from a buffer or from a file, all the data is already there. So if you have to reopen that and then have the 8-byte indices into that one and the length, it might just not be optimal. But if you actually look at this, the only strings we are concerned about are like counted just 20. There are 20 unique words that we actually need to store here. On that regard, obviously, history already sort of given us a tool to do this, and it's basically called string interning or array interning. Doing this in D is pretty trivial. I have a thing I call the small string index. Instead of size t's, it's a uint of the index and the length. And then there is a struct called the string interning thing. In it is the string itself, which is basically going to be a concatenation of all the strings that we want to store. Then there is an array of indices that get used to point into that string. And then there is a map to basically do the uniquing of them. If you then want to insert a string into this thing, you pass in the string, you check if it's already in the map. If that's the case, you dereference the index already stored. If it's not in the map, you create a new small string pointer, get the current length of the string, because that's going to be your start index into your string map. You get the length of the string, because that's going to be your length. You append the string to the string of the string index. You append the index, then you just return the index and you're done. By this way, you're compressing the strings that you actually want to store. You also have something that you can write to memory and then return. Or write to disk, and then reopen and have that. And also, this is actually, for me personally, the first real use case for const. When you reload the string interning thing from disk, you wouldn't reload the map, meaning you can no longer insert any string, or the information that needed to insert data into the string is lost. But insert is the only non-const operation here. So if you then have it const returned from disk, well, you have your constant string interning thing that you can index into, but you're sort of safe by const to do any errors with the data inside. So I find that really useful. Obviously, the construction of this thing is very slow, but if you know that there's a limited amount of strings that you have to read many times over, this is most likely going to be, or extremely likely going to be quicker, because the amount of data that you need is a lot less. And also comparing if two strings are the same is just a uint comparison. That's probably as quick as you can get. So first lessons first, measure first, and also think about what you want to measure. Obviously, I measured the wrong thing, but I learned afterwards what I wanted to measure. So it's definitely an iterative process. I hope you can see why parsers, AST, and visitor generators are fun. I mean, you put in a bit of grammar, you put it into it, and you get a lot of code out, a lot of value out. I've seen it time and time again in presentations as DConf, generating larger programs from a bit of input is the thing. And I haven't really seen it in other languages as much. So probably before measuring, the first thing is how can we do a tiny bit and get a lot out with the. Also, data-oriented design isn't really a new thing. I mean, if you look at pretty much any C program from the 1990s, you will find some very size-optimized buffer with weird indices into it, and you can't really follow what's going on. But for most cases, I bet it's some data-oriented design, because the engineers realized, hey, we have limited bandwidth to our memory, we have limited caches, and we have to make it fast because we have some hard time constraints on what we are trying to do. One thing I find very interesting and is quite often helpful to think about. So in the field of databases, database normalization is really still a thing. But it's mostly used to make sure that you don't have inconsistencies in your data, so that you don't store somebody's telephone number in 15 places and you read the wrong one every time. It's more about that part. But also what results from it is that quite often you get less data that you actually need to store without losing any of the information. And they're interesting concepts to connect different pieces, because everything is stored in tables. And usually what I find is that when you get to one of the higher normal forms, you basically already compressed and organized your information in a way that you're also reading it, which from sort of the intro realizes or gives you a way to get quite a bit of performance into there. Just in general, I think we ought to more often look into the past for inspiration. I know large language models are all the rage now, but database normalization has been here for 40 plus years, and it's still an extremely valuable tool that will likely yield, at least performance-wise, a lot more performance than large language models will ever yield. And that goes in many domains. Like, I mean, just realizing how little compute and memory power they had to get a rocket to the moon and all the calculations they had to do. They had to be smart and resourceful about the resources they had. And there are things to learn there. A link to the thing, and I'm at the end, and I'm, 10 minutes quick. Yeah, a bit early. So, question times.
I have a question about the data usage. So you gave the example of like data normalization and keeping track of repetitive used strings to keep in like a map, so you don't have to keep storing them again and again.
Yeah.
And while that reduces the total volume of data, you can think of this as walking along the same path as something like the zip program. So zip also reduces the total amount of data, but the amount of data you have to store at the moment of your processing, what fits in the CPU cache, is bigger because you keep having to jump to your index of the total thing of strings. So zipping a file is slow. Now, when you're parsing a file, you may be looking at keywords like while or whatever, or with capitalization, without capitalization, but you keep indexing the small piece of the file that you're looking at right now. So it's in total more data, but it's faster for the CPU because you don't have to keep looking it up or go into a cache or anything. And then the second question is, do you have an opinion on a D library called pegged, which seems I've used to great success? I'm curious what your opinion is.
For the first part, I would most definitely not store the while in the string map. For that, it's just an enum as its keyword. So you're not storing any value for that at all. But yes, you're right. It's more about like how often are you reading the text there and what are you doing with the text ultimately. Obviously, for construction, as I said, that is going to be way slower, because you have to look up the map and then all do the things. And obviously, as you said, you're also going to get cache invalidations when you index it again. Like as always, it's a trade-off, and you need to know what you're trying to measure and what you're trying to improve. I think sort of the more interesting bit there is, especially for programming languages, like after you have parsed it once, chances are that you have to actually parse it again are very slim. Because like how often does stdio.d change, right? But you have to reparse it every time. And if you could just memory blip it into existence, and that part at least is gone, or that part at least you don't have to do. And then also for the semantic phases, if you sort of get the outputs of the visitors, and that gets stored just as a memory or gets loaded as a memory blip, that is obviously going to be faster than redoing it again. On packed, I used it, but I alluded to it a tiny bit. The thing I don't like the kinds of grammar they accept, because I think as a human, LL1 is as difficult as I can understand. So recursive descent is sort of my drug of choice. And the red part, or the, the packed parsing algorithm is a lot more complicated. Also, the ASTs are not so typed that from the name itself you can see that you have an operation definition or a fragment definition. You can't see that. And sort of the probably most important bit about that I don't like is that it is a compile time thing. So you don't get code completion on that, at least not now. Where's Jan? Probably have to talk to him about that. So, but it works. And if it works for your use case, most definitely use it, but I had sort of other requirements, but then also I found this to be fun. And obviously that is a really good reason to do it yourself again.
Were there some performance numbers on the on your Lexing's part, the less fun thing that you did at the end? I noticed you did a bunch of data-oriented optimizations there, and I was wondering if you had some performance deltas or comparisons on the Lexing.
Unfortunately, my data-oriented design with structs and array was slower, about 20%. But I sort of measured the wrong thing and didn't really look before into what was going on, and it's basically all Lexing that takes the time.
Okay, so that was incorporated in the 20% numbers. The Lexing wasn't broken out parsing. That was the combined number. Okay, thanks.
So another advantage that I would expect from storing a tree as a flattened in an array, I would assume, is that you can pre-allocate the array instead of allocating each node one by
that's absolutely, and that's sort of one of the things I looked into yesterday a tiny bit, But on the surface here, for the comparison, I found that to be cheating a bit, right? I could have looked at the parse result and say, hey, okay, I'm needing like 20 elements here and 30 here, just pre-allocate and be happy and sort of beat the old thing. But most definitely in production, you would do that and probably have sort of a heuristic from saying, okay, I'm having an input of, 16,000 characters. Most likely this is going to be how much memory I'm going to have.
All right, we have a question from Ricky on the internet. Is there no UEX31 support?
Come again?
UEX31 support? Yes, no?
No. Pull requests welcome.
So just to be clear, like when you implemented the array-like tree, so the Lexer is the same, right? Did you have to modify? So the 20% is coming from that. It's not from.
Yeah, and that's sort of the interesting bit. On my home PC, actually, I sort of got like a 2 or 3% improvement. But the last couple of days, I was using this laptop. The optimizer in LDC is doing something I can't explain. Like for whatever reason, it sort of, is smarter with pointers than it is with indices into an array, which totally baffles me. I really don't know why, and hopefully Martin or somebody else can explain to me why.
So I don't know exactly how the code looks like, but is it possible that you're allocating the structs and then, on the stack, and then you're just copying them into the array? Because if you're passing them to functions and if it's not by ref or something, that might be it.
I mean, I'm doing that. That could be a possibility, but like compiling optimized, I would assume it's sort of optimizing that away a bit. I mean, it's definitely, I could check that relatively quickly. Instead of doing that, the class-based one has to basically malloc the space for a class, right, and sort of copy that into there. And I would hope and assume that that is going to be slower by default than, copying a struct, maybe.
It really depends on what you're doing with the struct from multiple. I mean, if you're passing by value, the struct to different functions and so on, I don't know.
Yeah, but for the visitor, I'm passing by ref. So there I'm not copying it. And also the visitor that counts the occurrences of the nodes, that was like 0.1% of the whole runtime. So in both cases.
I know why it's got slower. Yeah, I'm not surprised at all. Basically, I'm glad you had fun, but that was a very stupid thing to do. If your Lexer and parsing got 20% slower, and Lexer was the most part of it, it means your parser got like 3 times slower, and I'm not surprised. Absolutely, because you are grouping the wrong things. You're accessing. You need to look at which data you're accessing in the memory. And when you're working with AST nodes, if you're looking at, say, addition, you are not interested in what will be the next addition and then the next addition. Or if you see a string, you're not interested in what will be the next string in the program. You're interested in what will be the arguments of this particular node. So you need to group in the memory not different types of nodes, but you need to group the data of one particular node and then another node. So basically what you need to do to use cache, to make it cache friendly, you need to a different allocator that stores things that created at the same time at locations that are basically close together, like a bump locator. So and with your approach, basically you're grouping in memory their own unrelated things. So you are causing yourself to have even more cache misses, and we see it in your data. You increase number of cache misses, and also previously your program just chased some pointers, and now instead of chasing pointers, you do first array bounds check, and then basically the same chase pointers. So you added bounds check into every pointer access. So of course it is slower. It's obviously slower. I'm not surprised at all.
I absolutely agree on that part on the accessing, but that actually hasn't changed at all. And on the construction side, I would have assumed that that's not really that relevant. And then sort of the follow-up question is, I thought about that as well a bit, and you basically have like a binary heap in the memory, but it's not definitely binary because obviously you can have multiple nodes. And then unrolling basically what I thought you would have to do is have a node that has the maximum number of indices, which then would lead to most of the time, most indices would be unused. And I wanted sort of to avoid that. I'm not quite sure how to square all those different requirements there, and probably we can, looks like you have looked into that a bit more and maybe can give me more information.
I have been trying out using a tree data structure with indices as well. And what I found annoying was instead of, with pointers, you can pass them to a function and then that function can call a method on it, returning a new node, and you can go like .next. But with indices, you every time have to make sure you have also the array passed, and then the user of that index has to index the right array. But recently I found a C++ library which it stores indices internally, and then it hands out tuples of a pointer and an index, so you can still call methods on it. So my questions are, have you found the same annoyance, and have you explored similar solutions?
I haven't found the same annoyance, but what I do in the visitor is instead of passing down the index, I basically pass down a ref. But then obviously you have to make sure that you don't store the ref somewhere. I mean, you technically could, and you could also compute the index from the ref and the array. But yeah, I sort of had that annoyance a tiny bit, but in this regard, not that much. But I can definitely see that being annoying rather quickly.
Just to reiterate what the previous commenter said, I think this is a classic case of malloc having natural locality, since the calls to malloc are for things that are related and next to each other, and then you transform it into something that is not type-based. But I think it would perform better if all the nodes were in the same big slice of memory. And this is why with a custom allocator, sometimes you end up being slower than malloc because you didn't preserve some locality properties you already had.
Okay, yeah. I mean, it's definitely worth a try.
Well, thank you, Robert.
Thank you.